The conservation of energy, also stated as the conservation of electrical power, states that the power dissipated must be equal to the power supplied of the circuit. That is, if our circuit is supplying 8 watts, we must be dissipating 8 watts. Recall, our power is equal to our voltage times our current. We can neither create nor destroy our charge carriers, and our voltage potentials must balance within our circuit. That is, our circuit cannot supply more energy that's being dissipated, nor than we can dissipate more energy than what is being supplied. Using our passive sign convention, we want to determine if the following circuit obeys the conservation of energy. To the left, we have a table that's giving us our voltage and current values based upon what's drawn in the schematic on our right. Element A has a voltage potential of 120 volts, and IA is equal to minus 10 amps. Element B has a voltage potential of 120 volts, and a current of 9 amps. Element C has a voltage potential of 10 volts and a current of 10 amps. Element D has a voltage potential of 10 volts and a current of 1 amp. Element E has a voltage potential of minus 10 volts and a current of minus 9 amps. Element F has a voltage potential of minus 100 volts and a current of 5 amps. Element G has a voltage potential of 120 volts and a current of 4 amps. And lastly, element H has a voltage potential of minus 220 volts and a current of minus 5 amps. For us to solve this, we have to individually analyze each element and determine if it's supplying or dissipating energy. To begin, let's start with element A. Element A is drawn in a passive sign convention where we have 120 volt potential across the element and we have minus 10 amps running through. That would say we'd be dissipating minus 1200 watts, or if we flip the direction of IA, our current would be going from a low potential to a high potential. That is, element A would be supplying 1200 watts. If we go to element B, we see this is drawn in the active sign convention, where we have a voltage potential of 120 volts and we have a current of 9 amps running through. Thus, we're supplying 1080 watts. If we go to element C, this is drawn with respect to our passive sign convention. We're going from a high to a low potential, i.e. a potential of 10 volts, and this element is carrying 10 amps. Thus, we are dissipating 100 watts. If we go to element D, this is drawn in an active sign convention. We are going from a low to high potential, carrying 1 amp. Our potential is 10 volts, thus our power supplied is 10 watts. If we look at element E, this is drawn in accordance with our passive sign convention. We're going from a high to a low potential, and our current IE is running through. Now we note that both our potential and our current have minus signs associated with it, so we can flip the polarity of our potential as well as the direction of our current, and thus we're dissipating 90 watts. Element F is drawn in accordance with our active sign convention. However, we see our potential minus 100 volts flips our polarity. That is, IF is entering at our positive terminal and exiting our negative terminal. Thus, we are dissipating 500 watts. Element G is drawn with respect to our passive sign convention, and thus we are dissipating 480 watts. Lastly, we have element H, which is drawn with respect to our passive sign convention. We have a minus voltage potential and minus current. That is, we can flip the direction of our current as well as flip the voltage potential across our element. Thus, we still have a passive element and we're dissipating 1100 watts. Now, for us to determine if our circuit is obeying the conservation of energy, we have to sum our power supplied and sum our power dissipated, and they should be equal. In doing such, let's sum our power supplied. Elements A, B, and D are supplying power, and the total power supplied is 2,290 watts. Elements C, E, F, G, and H are dissipating power, and we are dissipating a total of 2,270 watts. These two values are not equal. That is, our circuit is not conserving energy. We could troubleshoot and recognize that if we switch the direction of current of element D or its voltage potential across, that then our circuit will obey our conservation of energy. For element D is currently supplying 10 watts, however, if we dissipated 10 watts, we'd have 2,280 watts supplied and 2,280 watts dissipated.